student. I am Om Prakash Dubey, chemistry faculty. In this class I am going to discuss ionic product of water and the degree of dissociation of water and the equilibrium constant for the dissociation of water. Like water in solution, it dissociated, it is also called the autoprotolysis of water. Water in this equation, water itself acts as an acid as well as a base. This H2O accepts H positive ion from this water and forms H3O positive and OH minus, and this equation can also be written as 2H2O, it gives to H3O positive and OH minus, and this equation can also be written as H2O gives to H positive and OH minus. Let us, if the concentration of water in this solution in the pure water is C. C is the concentration of the water. The initial concentration of the H plus ion and the OH minus ion in this pure water is 0, 0. If the degree of dissociation is alpha, then this water molecule dissociated C alpha, and the H plus ion formed in pure water is C alpha. The OH minus ion concentration in the pure water is C alpha. The concentration at the equilibrium of these species are C1 minus alpha, C alpha and C alpha. Now the equilibrium constant for the dissociation of water is H plus ion multiply the OH minus ion upon the concentration of water. Since as we know the concentration of pure water is taken to be 1 during writing the equilibrium constant expression, because its concentration do not depends on the amount. Now the equilibrium constant for this dissociation equilibrium multiply the concentration of water, which is equal to 55.56, is equal to the H plus ion concentration multiply the OH minus ion concentration. This product of the H plus ion concentration and the OH minus ion concentration is also called the ionic product of water, and the constant is ionic product constant is written by Kw, represented by Kw, and the value of ionic product of water is constant at the constant temperature at 25 degrees C, that is at 298 Kelvin. The ionic product constant for water is 1.0 multiplied 10 raised to the power minus 14 moles per liter raised to the power 2. It means the H plus ion concentration multiply the OH minus ion concentration is equal to 10 to the power minus 14. That means in any solution, in any aqueous solution, the product of the H plus ion and OH minus ion is always constant at 25 degrees C, that is equal to the 10 raised to the power minus 14. As the temperature changes, the value of ionic product constant for the water changes. As the temperature increases, the value of K also increases, the value of Kw also increases. The dissociation or the ionic product constant increases. Like in case of pure water, if the pure water is present, then the H plus ion concentration and the OH minus ion concentration, both the concentrations are equal, and as we know the product of concentration of H plus ion and the OH minus ion is 10 to the power minus 14, and if the concentration of H plus and OH minus are equal, then it is equal to the 10 raised to the power minus 7 moles per liter. That means in pure water the concentration of H plus ion and the OH minus ion is equal to the 10 raised to the power minus 7 moles per liter. Now calculate the degree of dissociation or the percentage dissociation of water. For the calculation of percentage dissociation of water, since the concentration of pure water is 55.56 moles per liter, it do not depends on the amount of the water present. If the concentration is 55.56 moles per liter and the H plus ion concentration and OH minus ion concentration both are equal in pure water, and which is equal to the C alpha, and it is equal to the 10 to the power minus 7, then we can calculate the degree of dissociation of the water, and which is equal to the 10 to the power minus 7 upon the concentration 55.56, which is equal to 1.8 multiplied 10 to the power minus 9. The degree of dissociation of water is very small, that is, it is a very weak electrolyte. Percentage dissociation, you can see 1.8 multiplied 10 to the power minus 7%. Now calculation of the Kc, the equilibrium constant for the dissociation of water. From here we can calculate the dissociation constant of the water. The dissociation constant is the product of concentration of H plus and OH minus upon the concentration of the pure water, and the concentration of pure water is constant, which is equal to 55.56. By taking 10 to the power minus 14 upon the 55.56, the equilibrium constant for the dissociation of water, it comes 1.8 multiplied 10 to the power minus 6. That means the equilibrium constant is equal to 1.8 multiplied 10 to the power minus 6 for the dissociation of water. In this session, I am going to discuss about pH and pOH of solution. pH and pOH of aqueous solution. The pH of solution and the pOH of solution is defined as, now the pH of solution, which is defined as negative logarithm of H plus ion concentration. Now this equation can also be written as log 1 upon H plus ion concentration, and from this equation we can see the pH of solution and the H plus ion concentration are inversely related. Inversely related, that means if the H plus ion concentration in the aqueous solution increases, then the pH of solution decreases. Now we can say if the H plus ion concentration in the solution increases, the pH of solution decreases. And similarly, we can also determine the pOH of solution, and the pOH of solution is defined as negative logarithm of OH minus ion concentration, and this equation can also be written as log 1 upon OH minus ion concentration. And again, the pOH and the OH minus ion concentration are the inversely related, that is, if the OH minus ion concentration increases, the pOH of solution decreases. If the OH minus ion concentration increases, the pOH of solution decreases. From these two formulas we can calculate the pH and pOH of solution. That is, if we can calculate the H plus ion concentration, then we can also calculate the pH of solution, and by knowing the OH minus ion concentration we can calculate the pOH of solution. Now these formulas are for the dilute solution, and it is not applicable for the highly concentrated solution, because in case of the highly concentrated solution, the effective H plus ion concentration is less than the exact H plus ion concentration or the expected H plus ion concentration, because of the interionic attraction in case of the highly concentrated solution. Now in the dilute solution, the H plus ion concentration, the effective H plus ion concentration is equal to the exact H plus ion concentration. So we can calculate H plus ion concentration, and by knowing H plus ion concentration or OH minus ion concentration, we can calculate pH and pOH of the dilute solution. In case of the concentrated solution, for concentrated solution, this formula is not valid for the calculation of pH and pOH, because the H plus ion concentration expected is not equal to the actual H plus ion concentration. For concentrated solution, for concentrated acidic solution, or for concentrated basic solution, the pH of solution is defined as the negative logarithm of activity of H plus ion, or the pOH of solution is negative logarithm of activity of OH minus ion. What is the activity of the H plus ion or activity of the OH minus ion? And this activity of an ion, either H plus ion or OH minus ion, it is defined as the product of activity coefficient and the H plus ion concentration, Similarly, the activity of OH minus ion concentration is defined as the activity coefficient of the OH minus ion and the concentration of OH minus ion. Now for the dilute solution, the activity coefficient for the ions, either H plus ion or the OH minus ion, the activity coefficient for the dilute solution is 1 nearly equal to 1. Therefore, the activity of ions, that is H plus ion, is equal to the concentration of H plus ion for the dilute solution. Then for the dilute solution, we can calculate pH and pOH of the solution from these two formula. But for the highly concentrated solution, pH and pOH of solution is calculated by knowing the activity of H plus ion or the activity of OH minus ion. Activity of H plus ion and the activity of OH minus ion is calculated by knowing the activity coefficient of H plus ion and the OH minus ion. The activity of H plus ion and the activity of OH minus ion can be calculated by using activity coefficient, which is nearly equal to 1 for the dilute solution, and for the concentrated solution, the activity coefficient either for the H plus ion or for the OH minus ion, it is less than 1. And the reason for the activity coefficient which is less than 1 is the interionic attraction in between the ions in the solution. That's why the activity coefficient is less than 1. That is the activity of H plus ion in case of the concentrated solution which is less than that of the H plus ion concentration. Then we can calculate pH and pOH for the concentrated solution by using activity of H plus ion and the activity of OH minus ion. In this session, I am going to discuss about the pH scale, how we can calculate the pH and pOH of solution, and how the pH scale varies with the temperature. Now the pH scale, simple, from the pure water, we can write the water which is dissociated as H plus ion and the OH minus ion, and the ionic product of water, which is Kw, is equal to the H plus ion concentration multiply OH minus ion concentration. And at 25 degrees C, the value of Kw, that is H plus ion concentration, OH minus ion concentration, that is equal to 10 raised to power minus 14, which is Kw. Now taking both sides log H plus ion concentration, OH minus ion concentration is equal to log 10 raised to power minus 14, which is log Kw. Now taking both sides negative, minus log H plus ion concentration minus log OH minus ion concentration minus log 10 raised to the power minus 14, and that is minus log Kw. Now we can write minus log H plus ion concentration is pH, and the pH and pOH of solution, which is equal to 14, and that is equal to pKw, and that is at 25 degrees C. If the temperature changes, the sum of pH and pOH changes. Suppose at 60 degrees C, the value of Kw is 10 raised to the power minus 13. Then the pH plus pOH of solution, and that is equal to 13. That means if the temperature changes, the pH scale changes. At 25 degrees C, the pH scale varies from 0 to 14, but at 60 degrees, the pH scale varies from 0 to 13. That is, if the temperature changes, the pH scale changes. Now, for pure water, see, the H plus ion concentration and the OH minus ion concentration in the pure water are equal. The H plus ion concentration and the OH minus ion concentration in case of pure water is equal. We can write H plus ion concentration, OH minus ion concentration, which is equal to 10 to the power minus 14 at 25 degrees C, and H plus ion concentration raised to the power 2 is equal to 10 raised to the power minus 14. and the H plus ion concentration is equal to 10 power minus 7, that is minus log H plus ion concentration is equal to minus log 10 raised to the power minus 7, that is pH of solution is 7. That is, in case of the pure water, the pH of solution is 7, that is H plus ion concentration and OH minus ion concentration both are equal, since the pH and pOH both are equal, and that is equal to 7. That means the H plus ion concentration and the OH minus ion concentrations are equal, and if the H plus ion concentration is equal to the OH minus ion concentration, the solution is neutral. The solution is neutral. That is, if pH is equal to pOH, and that is equal to 7 at 25 degrees C. These all calculations are carried out at the 25 degrees C. If H plus ion concentration is greater than 10 raised to power minus 7, that is the pH of solution is less than 7, the solution is acidic. And if the H plus ion concentration is less than 10 raised to power minus 7, the pH of solution is greater than 7, that means the solution is basic. That means if the pH of solution is known, we can determine whether the given solution is either acidic, basic, or the neutral solution. I am going to discuss how to calculate the pH of polybasic acid or polyprotic acid. Taken an example of dibasic acid H2SO4, which dissociate and gives 2H positive ion to the aqueous solution. The question is, calculate the pH of 0.01 m H2SO4, and the first dissociation constant is given, which is much greater than the 10 raised to the power 2. That means it is assumed to be dissociated almost completely. And the second dissociation constant, which is less than the first dissociation constant, but the second dissociation constant is not much very small. That means the second dissociation also contributes H positive ion, that is proton, to the aqueous solution. Now the H plus ion concentration total in the solution in this case is equal to the H plus ion concentration produced in the first step, and second step also contributes the H positive ion. In the first step, H2SO4 dissociated almost 100%. The concentration of H2SO4 is 0.01, the initial is 0.0, and if it dissociated almost 100%, 0.01, it consumes almost completely 0.01, and it gives 0.01 m H positive ion and 0.01 m HSO4 minus. The concentration of H2SO4 in the solution is 0, the H plus ion concentration is 0.1, and the HSO4 minus is 0.01 m. Now the HSO4 minus also dissociate in aqueous solution, and it gives H plus and SO4 2 minus. The K value is not much smaller. That's why the H plus ion obtained in the second step cannot be neglected. In the second step, HSO4 minus dissociates into H plus and SO4 2 minus, and the concentration of H plus ion is HSO4 minus is 0.01. The H plus ion concentration in the solution is 0.01, which is obtained from the first dissociation of H2SO4, and the concentration of SO4 2 minus ion is 0. If it is assumed that the HSO4 minus dissociated X out of 0.01 m, then the H plus formed in the solution in the second step is plus X, and the SO4 2 minus, it forms plus X. In the aqueous solution, the HSO4 minus remains in the solution is 0.01 minus X. The H plus ion in the solution becomes 0.01 plus X. SO4 2 minus is X. And the second dissociation constant is given, from which we can calculate the H plus ion concentration, the value of X. From the second dissociation constant, we can write the dissociation constant expression, which is H plus ion concentration multiply SO4 2 minus ion concentration upon HSO4 minus concentration. The K value is 1.2 multiplied 10 to the power minus 2 and the H plus ion concentration is 0.01 plus X. The SO4 2 minus concentration is X and the HSO4 minus concentration is 0.01 minus X. In this case, X cannot be neglected because the dissociation constant is not much smaller. Calculate X. The value of X comes 4.5 multiplied 10 raised to the power minus 3. And if X is calculated, then the H plus ion concentration becomes 0.01 plus X, and which is equal to 0.01 plus 0.0045, which is equal to 0.0145. Now the H plus ion concentration becomes 1.45 multiply 10 raised to the power minus 2. Taking both sides minus log H plus ion concentration, which is expression of pH, minus log 1.45 multiplied 10 raised to minus 2, which comes approximately 1.84. The pH of this 0.01 m H2SO4 solution is 1.84. In case of the polybasic acid, which the second dissociation constant is very small as compared to the first dissociation constant, then the H plus ion comes from the second dissociation can be neglected. But in case of the strong acid, which has the K value, K2 value larger, that is not much smaller, the H plus ion produced in the second step cannot be neglected and the pH of solution can be calculated by this formula or by this concept. Thank you.